Welcome. We're going to do our Stats Medic lesson 12.1 day 3 together. So you're going to need this sheet and your calculator. So let's dive in. Here's my test. Oh, look, I can write on this. So here we go. Mrs. Gallus is wondering if there's a relationship between GPA and SAT score. She took a random sample of 9 out of her 101 students and she recorded their GPA and ACT score. So let's look here at what's important for us to take note of. So we've got a random sample of 9. Right, out of 101 students, and we are recording their GPA and their SAT score. So what's important here? Well, we know that little n is 9. We know that big N is 101. And we have two variables. We have variable 1, variable 2, and they are both quantitative variables, and we're trying to determine if there is a relationship between the two. So what are we going to do? I think we're going to plot our data in a scatter plot and do an LSRL. So we've got our data here. We have our student number. That's an identifier. It's not a variable. And we have our two variables. So GPA is going to be our independent variable. So that would be like our X variable, and ACT like our Y variable. So why don't you pause the video and enter your GPA in list 1 and enter your ACT scores in list 2 in your calculator. Okay, with that being done, what relationship would you expect GPA and ACT score to have? Well, I think it would be reasonable to expect that as GPA increases, that ACT will increase. And if one variable gets bigger as another variable gets bigger, then what we're expecting is a positive relationship. And it might be reasonable to assume it's a positive linear relationship. Okay, not quite sure about that. So that would be a good way to answer those questions. So here we go. We have a mini tab output as well as graphs of our data. So as we look at this, our predictor is our X variable. So X is our GPA. Its coefficient would be our slope. So that's our B1. The coefficient of our constant would be our y-intercept. So that's our B sub 0. We have the standard error coefficient. So this would be our standard error of our slope. We have r squared, which is 0.828 as a decimal, and we could find r by taking the square root of that. We also have this, which is our standard deviation, right? So it's our standard deviation of our y's, right, or our residuals. Okay. Now let's look at the graphs that they provided for us. What's this first graph? Well, that's our scatter plot. And we have two axes. Since X is our predictor, our independent variable, the horizontal axis should be GPA, and those numbers make sense for that. And our vertical axis should be our ACT, right? So you know those numbers as ATC scores. So the second plot is our residual plot. And residual plots can plot Y values against residuals or X. These numbers are GPAs, so that's going to plot your residuals for Y against your X variable. And then finally, we have a dot plot of our residuals. Okay, so those range from -6 to 4. So our first job is to find the LSRL. Go ahead and pause the video You've done this before, and find the LSRL for X and for Y, as you've got them in your calculator. Okay. So let's write that, and I'm actually going to use words or letters, I guess, in this case. So we have y hat, but our y is our ACT, so I'm going to write that as ACT hat is equal to our A, which is our y-intercept, right? And that y-intercept was 1.201, so 1.201 plus our slope, right? And our slope is 7.507 times our x variable, which here is GPA. Okay. So we also had our R squared is 0.828, so we're given that. And if we take the square root of 0.828, we get an R value of 0.910. And we know that that would be positive because our linear regression line has a positive slope, and the sign of your correlation is always the same as the sign of your slope. Okay, so we got that much. Let's go on, and we're going to build on that. And we have a question, and it says, do the data provide significant evidence that there is a positive linear relationship? Well, what do we do when we're trying to find evidence? We do a significance test. So here we go. State, plan, do, conclude. Aren't you glad that this isn't new and you know exactly what to expect here? You guys have learned so much. So here's our state, right? And our state is that we want to test the following hypotheses. Where our parameter is beta 1, which is the true, right? So keyword there, the true slope of the population, right? Another keyword here, LSRL, relating GPA and ACT score. Our statistic is going to be little b sub 1, which is the slope that we get from the LSRL that was constructed from our data, and that was 7.507. Our null hypothesis is going to be about the slope, right? We're doing significant test for slope, and it's about the true slope. So our null is that our B1 is actually, well, let's go back and talk about this. We're trying to find if there is a positive linear relationship. So our null would be that there's not a positive linear relationship, which for us, we're going to always start with 0. So the null is that if there is no linear relationship, the slope would be 0. Our alternative will be that the true slope shows a positive linear relationship, so it would be greater than 0. For a significance level, we're not given one, so let's use alpha equals 0.05. Okay, so there's our state. In our plan, right, how are we going to test that hypothesis? Well, in this case, we are going to do a one sample. Right? Our data came from one sample of 9 students. Right? We're going to take a one sample t-test for capital B. Right? So for our true slope. And we have our conditions. So conditions are our liner. For linear, right, our conditions address our scatter plot. Our linear is addressed by our scatter plot. So our scatter plot is approximately linear. And we also go by our residual plot. And our residual plot no leftover pattern. Let's go back and just look and see. All right, so in here we had our scatter plot, right, which definitely shows an approximately linear pattern. And then we have our residual plot. Now you might look at this and say, hey, wait a minute, I see a curved pattern here. But when we have leftover pattern, at least what we're going to see in this class is when we have leftover pattern, what you're going to see is that high, low, high. So if we had all our dots up here and then in the middle they were low and then at the end, right end, they were up high, that would be our curved pattern. With such a small set of data, we shouldn't be surprised that we're going to see what looks like a curved pattern if we follow those dots, right? Because it's not high, low, high or low, high, low, we would say there's no leftover pattern. Okay. So that's our L. Our I is independent, right? And we would assume that students' scores are independent, that knowing one student's score wouldn't tell me anything about somebody else's score. And we did take a sample without replacement, so we have our sample size, which is 9, should be less than 1/10 of our population size, which we know is 101, right? And a tenth of 101 is it's 10.1, and 9 is less than that, so that's a true statement. For normal, we're going to look at our dot plot of our residuals. All right, so let's go back and look at that. In our dot plot of our residuals, which is here, right, we see no strong skew or obvious outliers. Again, very small set of data, right, but that looks relatively symmetric, right, with nothing really outstanding that would warn us otherwise. So our dot plot of residuals, right, has no strong skew or outliers. Okay, so far we've looked at the scatter plot and the residual plot for linear. We've looked at our dot plot for normal. Right? And now we're going to look at equal standard deviation. So for equal standard deviation, right, L-I-N-E, we're going to refer back to our residual plot. Okay. And what we're going to look for on our residual plot is that the scatter doesn't increase or decrease as our x variable increases. All right, so we're looking for a random scatter of our residuals around our residual equals 0 line. So except for this dot here, we have pretty equal scatter. And again, such a small data set, we can see things stand out that wouldn't if there were more. But what we're going to address here is that from your residual plot, we can see that the residuals are randomly scattered about the resid equals 0 line. Okay, so finally for random, right, what we know is that she took a random sample. Okay, that's the longest part. The rest we're pretty used to. We're doing a significance test, so we have to find our test statistic. And our general formula for that is that our test statistic is going to equal our statistic minus our null over our standard deviation. So for us in this case, our test statistic is going to be a t-score, and that will equal our statistic, which is the slope of our LSRL, which is our B1 minus the null, and the null is that the true slope is 0, divided by, for standard deviation, we're going to use the standard error of B1. So plugging in the numbers we have here, t will equal 7.507 minus 0 over 1.29. Right, do the math on that, and we get 5.819. So go back, we're going to draw a very familiar picture of a symmetric curve. This is not a normal curve because this is not a normal distribution, but it's a t-distribution. Still 0 is in the center, and when we do a t-distribution, we have to give the degrees of freedom, which is going to be n minus 2, n was 9, so our degrees of freedom are 7. And what we're doing is saying, all right, we have a t-value which is positive, and it's 5.819, which is going to be pretty far right towards the tail. And we're looking for our p-value, which is going to be the area to the right of that line. Right? And that's our p-value that we're looking for. So our test statistic, right, just to reiterate, is our t, which is 5.819, and we want to find our p-value. So one way to do that is to do a TCDF. Right? So we can do a TCDF with a low of 5.819. Right? That's our low. A high of something really high, so you can do infinity or 1,000, and then degrees of freedom is 7. So go ahead and pause the video, put that in your calculator, and let's find that p-value. Okay, now on your calculator you see 3.25. Be careful, follow that all the way to the right, and you see E-4. Right, that means we've got to move our decimal place 4 places to the right. So we here get a p-value of 0.000354. Okay. So before we draw our conclusion, let's just look at doing this on the calculator. Right, so if we do our calculator, you might want to do this with me. So go to Stat, and then go to Tests, and scroll down till you find, doing this with you, the linear regression t-test. So that's F, right, option F. So we're doing a linear regression t-test, right? Yesterday we did the interval. So let's go ahead and select that. And our X's are our GPAs. They were in list 1. Our Y's are our ACT scores. They were in list 2. Right? And then we put in our alternative hypothesis, which is going to be that our true slope is greater than 0. So make sure you select greater than 0. You can store your linear regression line, which means it's going to find that linear regression line for you. You actually don't have to do it separately. And then calculate. And it tells you it's going to give you a line in the form of y equals a plus bx with the slope greater than 0. Don't worry about the row. That's that little p looking thing. We're not using that. Okay, but this is what you're going to want to record from here. You're going to want to record your test statistics. So t is 5.818. Your p-value, so your p-value is 0.000325. Let's clean that up. That's I did that badly in both. So 0, 3, 2, 5, and your degrees of freedom. Right, so you want to make sure you record all 3 of those things. Right, this also gives you all the other information you would need, which we've already really recorded. So our final conclusion is, right, you should probably be able to say this with me, because our p-value is less than an alpha of 0.05. What do? We reject H naught. There is sufficient evidence to conclude there is a positive linear relationship between GPA and ACT scores for Mrs. Galla's students, right? The population was just her students. Okay, so just to finish up, what are our important ideas? Learning target number 1 would be that when we do this, our null hypothesis is always going to be that the slope is 0. Our alternative hypothesis will always be that the true slope is either not equal to 0, or that true slope is less than 0, or that true slope is greater than 0. As far as our test goes, our conditions, right, so this is learning target number 2. Conditions are liner, and you have those in notes already. Our do is a 1 sample t-test for slope. Our formula for t is the slope of our linear regression line minus the null, right? So actually that was b sub 1, different notation in different contexts. So b sub 1, which is usually 0. I think for us it'll always be 0. Except in a problem number 6, it might not be 0, over the standard error of your slope. Remember that you've got to always give your degrees of freedom, which are n minus 2. And yeah, and the other thing is just to think about using a TCDF. With your lower t, your upper t, and your degrees of freedom. Okay, that's it for us. And you should be able to finish this sheet on your own.